A race car reaches a straightaway going 140 kilometers per hour, then accelerates at 3.50 meters per second squared for 6.2 seconds. A. What is the car's initial speed in meters per second? So this is a simple dimensional analysis question. Dimensional analysis is a quick and easy way to convert units back and forth. In this problem, we are converting kilometers per hour into meters per second. The first step is to write down our conversion rates and our given value. So under the heading givens, I'm going to write down 140 kilometers per hour because that's our initial velocity. And its conversion rates into meters per second. So there are 1,000 meters in 1 kilometer, and there are 3,600 seconds in 1 hour. The next step is to set up the dimensional analysis fractions. Start by writing down your given/original value in its with its units and its appropriate part of the fraction. So if there is a per in the unit name, then you know that there will be one value in the denominator. So this is the case because it's 140 kilometers per hour. So the unit after the slash of the per is going to be the unit that is in the denominator to start out. So it's going to look like this: 140 kilometers per 1 hour. The next step is to set up the rest of your problem or set up the conversion rates. So when setting up your conversion rate fractions, you want to think about which setup will make it so the units that you don't want cancel out and the units that you're trying to convert to are the only ones that are left over. So we don't want kilometers or hours, and we want meters per second. So what we're going to do is we're going to use a little bit of algebra. If you have a unit in the bottom and a unit in the top of another fraction, then they cancel out because it is multiplication. So with that in mind, we're going to set up our first conversion rate of 1,000 meters per 1 kilometer. As we can see here, we have kilometers in the top of this fraction. So this means if we want kilometers to cancel out, we're going to want to put kilometers in the bottom for the when we set up our conversion rate of 1,000 meters per 1 kilometer. So it's going to look like this: 1,000 meters per 1 kilometer. As we can see here, we have kilometers in the top and kilometers in the bottom. So that means we can cross these out and not have to worry about them anymore. And then we're just going to do the same exact thing with our second conversion rate of 3,600 seconds per 1 hour. So hours in the bottom, that means we're going to put hours in the top. So multiplied by 1 hour over 3,600 seconds. Now that we have that and all of our units cancel out that we don't want, and the only units we have left are meters and seconds, all we have to do is plug this into our calculators and get our answer. So 140 multiplied by 1,000 multiplied by 1, and then that divided by the numbers on the denominator, so that divided by 1 times 1 times 3,600. And this gives us our initial velocity in meters per second of 38.89 meters per second. So velocity initial is equal to 38.89 meters per second. So the second part of this problem is, what is the speed of the car at the end of the 6.2 seconds? This is a kinematics problem, and kinematics is the study of motion. And fortunately for us, we can solve most of kinematics with this row of formulas right here. So when looking for what formula to use, I always look at my given values and my find values. So I'll write them down right here. We have a velocity initial of 38.89 meters per second. That's from the last part of the problem. And we have an acceleration of 3.5 meters per second squared. And we have a time of 6.2 seconds. And our find is the speed of the car at the end. So we know that our find is going to be velocity final is equal to question mark. So I'm going to separate these just so it doesn't get confusing. And so now that we have these values, we can refer back to our formula sheet, and we're going to want to keep an eye out for these symbols or letters. So looking at this formula sheet, we have a bunch with velocity. For example, that one, this one, this one, this one, this one. So we're going to want to look for our other values. They're right here. So we want velocity initial, acceleration, and time. And one that immediately sticks out to me is this one right here, because not only does it have velocity initial, acceleration, and time, it also has velocity final as its result. So this is definitely going to be our winner. So let's just write that down. So our formula is velocity final is equal to velocity initial plus acceleration times time. And now that we have our given values, we can just plug this in and get our answer. So velocity final is equal to our velocity initial of 38.89 plus, or meters per second, plus our acceleration of 3.50 meters per second squared, multiplied by our time of 6.2 seconds. 6.20 seconds. So now all we have to do is plug this into our calculators. If you have a scientific or graphing calculator, then you don't need to worry about PEMDAS. But if you don't, you're going to want to multiply these two values together first and then add the initial velocity. So that's what I'm going to do. I'm going to pretend like this is just a basic calculator. So 3.5 times 6.2. This pretty much gives us our increase of velocity. And then we add our initial velocity of 38.89 to get our final velocity of 60.59. So velocity final is equal to 60.59 meters per second.
No, I took a video. It just isn't saying that I don't have enough.
So the third part of this problem is how far did the car travel in that time? This is another kinematics problem, so we're going to follow many of the same steps as last time. First, we're going to write down our given and find values. So
where's that proper proof?
So we have a velocity initial from part A of 38.89 meters per second. We have a velocity final from part B of 60.59 meters per second. We have an acceleration of 3.50 meters per second squared. And we have a time of 6.20 seconds. And our find values, our find value is how far, so it's going to be distance or displacement. For this problem, they're pretty much the same thing. So find x, that's displacement. X is the symbol for displacement, is question mark, and D is question mark. So they're pretty much the same thing for our purposes. So next, we're just going to look at our formula sheet now that we have what we're trying to find and what we have. So let's do that now. So we're going to refer back to this most left row because these are all your kinematic equations. So immediately the one that sticks out to me is this one right here. X is equal to VI times t plus 1/2 AT squared. Just because we have velocity initial, we have acceleration, we have time. So this is definitely going to give us the answer we want because it yields X, and that's what we're trying to find. So let's write that down now. X is equal to velocity initial times time plus, sorry, that looks kind of confusing, but that's a t, that's a plus, plus 1/2 AT squared. So now that we have our formula and all of our givens, we can just plug it in and get our answer. So X is equal to our velocity initial of 38.89 meters per second multiplied by our time of 6.2 seconds. And then that added to 1/2 times our acceleration of 3.50 meters per second squared multiplied by our time squared. So 6.2 seconds squared. So now all we have to do is plug this in and get our answer. We'll get our calculator out. So let's just move this up. Oops, sorry. So 38.89 times 6.2 and then plus 0.5 times 3.5 times 6.2 squared. And we get 308.38. That rounds to 308.4 feet. So X is equal to 308.4 feet. Or wait, meters. Excuse me. Meters. But this isn't. So if you didn't like using that formula to solve this problem, you're in luck, because there's actually another way that we can solve this same problem. We can use a simple derivation. A derivation is when you combine two formulas to make one formula that will solve your problem in terms of your givens. So if we look back at our formula sheet, we see this extremely simple equation: average speed is equal to distance divided by time. So this is going to be the basis of our derivation right here. So average velocity is equal to distance divided by time. And then if we just solve for distance, because that's the find value that we're going for, by multiplying by t on both sides, we get distance is equal to velocity average times time. And then, so let's compact this a little bit to make it look a little neater. So with our new formula, d is equal to velocity average times time. And then we're going to refer back to our formula sheet because we don't actually have velocity average. What we have are velocity initial and velocity final. So we're going to look for a formula that gives us average velocity, and that's this one right here. Velocity initial plus velocity final divided by 2. So let's write that down. Velocity average is equal to velocity initial plus velocity final divided by 2. So this is where the derivation kicks in. In a derivation, you can take two equivalent values and just exchange a formula in for that value if you don't have that value and you have the values in that other formula. So that may sound confusing, but I'm just gonna do it for you and I think you'll pick up on it. So as you can see here, we have velocity average is equal to this. And then we have d is equal to velocity average times time. So if you think about it, d is equal to this because this is equal to velocity average times time. So that's all our derivation is going to be. It's going to be distance is equal to velocity initial plus velocity final divided by 2 times time. So all we did was replace this velocity average formula right here with velocity average because we had these given values and we didn't have average velocity. So if we plug this in, we should get the same exact answer as last time. So 38.89 meters per second plus 60.59 meters per second divided by 2 times our time of 6.20 seconds. And if we plug this into our calculator quickly, 38.89 plus 60.59 divided by 2 multiplied by 6.2. We get the same exact answer as when we use the formula. Straight from the formula sheet, 308.4 meters. So both ways work. It's more like a preference thing, but I thought I'd just show you both. So there you go. You get the same answer either way.